All right, guys. Thanks again for coming. This is Mr. Zawacki, and what we're going to be talking about today is what to expect on your upcoming DBA. Specifically for biology, we're going to be talking about the Module 5 DBA about evolution, and also anatomy, Module 4 about the cardiovascular system, heart, and blood vessels. All right, so those of you who are new to HVS or new to my course, what is a DBA? Well, we already know that. It's an oral exam in which you and I speak over the phone or in person. It's about 5 to 6 questions that cover main topics from the module that you are working in. You're allowed to use your notes as well. That's why it's very important to take notes over the module, but not the lessons themselves. So when you're doing a DBA, it's okay to review through your notes if you forgot a certain word or something, but you don't need to be working and clicking through lessons and just reading off of that. That's not really helpful to you learning the material. Answers should still be in your own words to prove you know what you're talking about. And the total point range is anywhere between 30 and 50 points. The Module 5 DBA for biology is 30 points. And the Module 4 DBA for anatomy is 35 points. When finished and if passed, you will go to the assessments area and type in the comments box the date and time of the DBA and 3 to 5 sentences about what we talked about. And then I'll also give you the password for the module test that you can take right after. So again, DBAs, guys, they're just oral exams. There's 5 or 6 questions. You can use your notes, but you should still try to explain everything in your own words. Then, they're worth 30 to 50 points, and if you pass it, you'll be able to get the password for the next chapter test. All right, so biology, Module 5. You guys definitely need to know what evolution is. And this is it. This is the definition of it. The change in features of a species over time. All evolution means is that species change over time. That's it. Every single species on Earth will adapt and change to better suit its environment. This happens naturally. And that's what evolution is, just species changing over time. Here is a good branched pattern of the elephant evolution. Started off believed to be one small species of elephant a couple million years ago. And then it evolved to become a little bit bigger, but then it branched off to form new species of elephants. As you can see, today there are only 2 species of elephants on Earth. About 10,000 years ago, there were 5 species of elephants on Earth, as you can see on this timeline. The current species of elephants on Earth are the Asian and African elephants. 10,000 years ago, at the end of the Ice Age, we also had the woolly mammoth, mastodon, and another elephant located in a tropical region. But they have since went extinct. So just to show you what evolution is, it's just a change in species over time. How does it happen? It happens in small changes to better suit that species over time. And it's usually in a branched pattern. All right, how do scientists know evolution actually exists? Well, there's proof. There's evidence behind it. Remember, it's called the theory of evolution. Anytime you see the word theory, that means there's a lot of evidence that backs it up, and it's been tested thousands of times. So it's a pretty strong statement if you see the theory of blank. So, anyways, here's your main evidence that supports it. Number 1, fossils. Just by looking at a fossil, you can see how a species has changed over time. And by looking at fossils, they can tell you how old they are. They can tell you their relative age. For example, if something is deeper than, if a fossil is deeper than a fossil above it, well, that deeper fossil is older than the one above it. That's called relative age. Or they can see how much carbon is in it and tell you the exact age. That's called carbon dating. Either way, fossils will show you how a species has changed over time. Homologous features is second. This is also comparative anatomy. Excuse me. Believe it or not, we have very similar bone and muscle structures as other animals do. We have the same number of bones, muscles, and tendons in our hand as a bat does in a wing, as a cat does in a paw, as a whale does in a flipper. All of these are the same number. So what does that tell us? Well, we're all closer related than what we think. And we've all probably adapted and changed just like the elephant did, all from common ancestors. So homologous features, comparative anatomy, that's more evidence that supports evolution. Vestigial structures is a huge one that supports evolution. These are body parts that no longer seem to have a function. Can anybody tell me some vestigial structures that we have right now on our body? You guys can type those in the chat box. What are some vestigial structures that we have? Good job, Cameron. Good job, Talea. There's two big ones right there. Tailbone, appendix. Now we still kind of need our gallbladder. That helps digest greasy foods. So we still use that a lot. Also, next time you look in the mirror and look at your eyes, if you look off to the edge of your, not the corner of your eye closest to your nose, but the corner of your eye away from your nose, you guys are probably doing this right now, but if you see a little, it looks like a little piece of almost like an additional eyelid. We used to have eyelids that used to close from left to right so we can see underwater. So that would be another thing that we used to have of a vestigial structure that you can only see a very small resemblance of it now. Also, there's another one. Muscles. There's muscles that some people can move their ears. I can't, but some people can. Those muscles are vestigial structures as well, because we used to move our ears to hear better in wild-like situations. So all of those are vestigial structures. And yes, some people have those, not everybody. Just like I can't move my ears, but some people can. Some people also will have that little additional piece of their eyelid off to the edges, and some won't. But that's all vestigial. Embryology is another one. We were all embryos about 8 months before we were born. All of us were. Well, so are other animals. Before they're born, they're also embryos. And if you look at a picture of an embryo of us, and you compare that to a mouse or a snake or a fish or a chicken, they all look the same. You can't tell them apart. So what does that tell us? Well, maybe all species begin to develop similarly. And we've also adapted from that same way. So embryos just show, literally what the animal looks like before it's born. And embryos look very similar amongst all living things. And then DNA is the fifth one. We know DNA is our genetic code. Well, what if I told you we're 99% the same DNA? It's billions of letters long. We have 99% the same code as a chimpanzee. We have 50% the same code as a tree outside. So what does that tell us? Well, we all living things have a similar genetic code. And also, that genetic code changes slightly over time. That's how you get new species. When the change in genetic code happens, that could result in a different looking species. So that's also proof for evolution. So I will definitely ask this question on the DBA, so just make sure you guys are aware of it. You need to know fossils, homologous features, vestigial structures, embryology, DNA, all of this is evidence for evolution. All right. Then in 502, you guys learned about natural selection. Natural selection is one way on how evolution can occur. Just one way. And it's summarized into 4 major parts. You have overproduction, you have variation, you have adaptation, and then selection. These are the 4 steps on how natural selection occurs. Overproduction's first. That means parents of wild animals will produce as much offspring as they can. As much as they can. Variation is next. Some species will look different than the rest. That could be good, that could be bad. The third step is adaptation. If it's a good thing, that means it's an adaptation. Adaptations are very important because they will allow for species to change and adapt. If that adaptation is a good thing, well, probably they're going to create more and more species just like them. And that's where you get the selection part, which is number 4. Over time, offsprings of individuals with helpful variation make up more and more of a population. That's what natural selection is. It's producing as much offspring as possible. Some of those offspring are going to be different. That's variation. If it's a good thing, that's called an adaptation, and that will cause the species to change over time. That's where you get the natural selection. Okay. I will also ask you about an example of natural selection. You can make it up or make up a real-life example too. This is a made-up one, but it also could be a real-life situation as well. An eagle or a hawk is going to prey and eat those mice. It looks like there's 2 versions. There's a tan-colored mice and a gray-colored mice. And a population of mice has moved into the area where the rocks are very dark. So due to natural genetic variation, some mice, are black, and while others are tan. Tan mice are more visible, so the bird is going to pick off those tan mice because it sees them easier. So it's going to eat them first. Only the surviving mice reach reproductive age. So these gray mice are going to reproduce. They're going to produce more and more of them. And you see more and more of them. Because black mice had a higher chance of leaving offspring than tan mice, the next generation contains a higher fraction of black mice than the previous generation. So to backtrack, they may have all been tan-colored mice at first. They may have been. But if they have a variation where maybe some are born gray, look what happens. Now, the gray ones have an advantage. The tan ones get picked off. So what do you think would happen to the tan version of mice in future generations? What do you think would happen? Yeah, they could go extinct, Catlin. There would definitely be much fewer of them because they're getting picked off. That tan version could be gone forever just because there's a better version now, and that version is being successful. So that's what natural selection is. Did that species of mouse change slightly over time? Yeah, that's evolution. Natural selection is just one way on how evolution can occur. So when you think of natural selection, think of this example and you'll be golden forever. All right, and then in 503, we got into primate evolution. And I explained this last time, but I'll explain it again for those of you who are here for the first time. First of all, question for you guys, does human evolution run on a straight line linear pattern, or is it more branched? What do you think? Good job, Ryder. Alana? Yep. Yep. Talea, Cameron, Paris? Good. It is definitely more branched. I know we've seen pictures or maybe graphics of a human evolving, or an ape evolving into a human. Well, that's not accurate. I wouldn't look at that. I wouldn't even consider that path. This is a more accurate depiction on how we evolved, this picture right here. So to show you, this is present time. Present time, there are 1, 2, 3, 4, 5 great hominid species on Earth today. There are 5. 3 million years ago, well, as you can see, there were 1, 2, 3, 4 species, as you can see on the lines. Well, going all the way back to 13 million years ago, there was this species on Earth that we have found in the fossil record that has very ape-like similarities and also human-like features as well. So it's kind of like an in-between type of species. It does not exist today. It went extinct 13 million years ago. But over time, some species of that very extinct species 13 million years ago, some of them, individuals, decided to go live in trees in a tropical area. Out came the orangutan species. Other species decided to stay more on land. And now you still have a similar species of today. Then, about 8 million years ago, this species down here, which is our common ancestor A, it eventually evolved to form a new species, common ancestor B. It looked pretty similar to A, but it was also a little bit more adapted, just like you saw in the mice example. And then, from that point, about 8 million to 7 million years ago, some species decided to live on land, but in the tropical forest. Out came the gorilla. Others decided to stay in a more temperate area, but not in the forest, in the Great Rift Valley near Ethiopia. And now we have species C. Species A, B, and C all look kind of similar. They're a little bit different over time. They look kind of similar. Well, then a species then began to live in a different area. And then out came another species that transformed into the chimpanzee or the bonobo, where we see in Africa today. Other species, the hominids, began to explore more of Earth. And that's where you get the Neanderthals that went extinct about 30,000 years ago, all the way to the human that we see today. So to put this all into perspective, we did not evolve from apes. We did not evolve from apes. We did evolve, all of us, orangutan, gorilla, chimpanzee, bonobo, human, we all evolved from a common ancestor that looked kind of similar to all of us 13 million years ago. Even more recently, about 5 million years ago, we evolved from a common ancestor that had all 3 of these characteristics mixed together. Over time, they separated out. But originally, we had a common ancestor 5 million years ago with the chimpanzee, bonobo, and human. So if you would go back in your family tree 5 million years, and you take a random chimpanzee and go back in its family tree 5 million years, we would have the same ancestor 5 million years ago. So I hope that explains how humans evolved as well from a common ancestor. We did not evolve from apes, but we all evolved from a common ancestor millions of years ago that has since gone extinct. All right, and then the last thing about 503, about the skulls lab that many of you guys are working on today, you need to know the differences of how the oldest skull evolved into our current skull? Well, the eyebrow ridge it used to be more outward, and now it's more inward. The teeth used to be much sharper, but now they're duller. The brain size used to be much smaller. Today it's much bigger and more adapted. Also, a jaw used to be much bigger and stronger. Today, not as strong. So, a question for you guys, and you can't really be too wrong on this answer because there's a couple correct answers. Why do you think these changes happen? This was our skull roughly a couple million years ago. Why did these changes happen to our skull today? What were some events that may have led to that? And yes, Scotland, technically, if you get a pet chimpanzee, they're technically your relative from 5 million years ago. If you get a pet dog, that's technically your relative from about 30 million years ago. So every living thing you can trace back to a common ancestor. Just our most recent common ancestor is the chimpanzee. So that's why they look most similar to us. All right, good job, Cameron. We didn't need those advantages of a strong jaw or small teeth. The environment could have changed. Yep, definitely. What else? What could have caused these changes for us? Yeah, we used our brain more. That's why it's becoming bigger and more adapted. Right, Catlin, we don't eat the same things in order to need those sharp fangs. We don't eat and pierce through skin and raw meat as much as we used to. So that's why our teeth are not as strong. Our jaw is not as strong. Eyebrow ridge, we used to live outside, right? Well, now we live in houses. So we don't need that much of a outdoor eyesight as we used to have. It's sad, but true. Our bodies are changing and evolving every generation. Every single generation, we're getting taller as a human race. We're also having bigger feet as a human race. And we're even losing some of those vestigial organs that a lot of us have. People are born today without appendixes. So there's a lot of changes going on even right now. You just don't see them because they're very small, and it takes time to do that. So as you can see, this change with the skull, that took millions of years. So it doesn't happen overnight. It happens little by little over generation and generation. And that's what evolution is, just simply species changing over time. Okay, very good, guys. All right, so that is it for biology for Module 5. Real quick, if you're here in Segment 1 for biology, if you're taking this during the second semester, as all of you guys seen this DBA before, make sure you tell me about science and what science is. What are some of the major branches of science, like chemistry, physics, biology? Also know about pseudoscience, how that's fake science and how that's different than real science. Know the steps of the scientific method. Know about the microscopes, compound light or scanning electron, and be able to tell the difference between them. Also know about the properties of water. Remember cohesion, adhesion, surface tension, to be able to discuss those as well. Yep, good job. And also, you guys, for biology, you should all remember this because it is going to be on your biology EOC coming up in about 4 months. So this is a little bit of a good review. So just make sure that you always keep that in mind. I don't have anybody in here for forensics. I'm not teaching that this year. Anatomy, Module 4, though, I might have 1 or 2 of you. The main parts of the heartbeat. Know about the first and second sounds of the heartbeat. The first sound is when it's relaxing. The second sound is when it's contracting. The sound you hear are the valves in your heart closing. Know about hypertension, which is high blood pressure, with causes that cause it. Know about the components of blood: red blood cells, white blood cells, plasma, and platelets. Know about blood plasma and what's found in it. Know the steps of hemostasis. That's where you get pet and you and you have to go through steps to stop bleeding. So make sure you know the steps on how hemostasis works for you to heal a cut. And then know about blood types. Remember A, B, AB, and O? Know the 4 blood types and know what antibodies they each have and who can donate and who can receive blood from. So pretty much look over all your blood facts, your heart facts, and your blood vessels. And that's pretty much all from Module 4. All right. Does anybody else have any other questions for me today? Okay, well, if you do not have any other questions, you're able to go on and continue working. Thank you guys again for coming. And then Cameron, you wanted the Module 2 questions for which course? All right, Catlin, thank you guys. Have a great day. And then, yeah, if you guys don't have any other questions, you are free to go, and I'll answer everybody else's momentarily. So thank you guys for coming, and hope to see you next week.